Hey guys, welcome back to another episode of Simuleos, the only channel on Twitch. Well, okay, it's a channel on Twitch. We typically do physics stuff, and today is one of those days where we do a lot of physics stuff. So, what are we doing today? Well, if you remember from yesterday, we spent a good amount of time working on our diagonalization stuff. So we were working on the QR decomposition method. Now here's the thing, we got pretty far. And we didn't quite finish everything though. See, the problem was that after working on it for like 2 hours yesterday, we still did not get to a point where we could really understand what the bugs were in the code that we had written. So I went online last night. I spent a good bit of time looking up more stuff about the QR decomposition algorithm, and I found a good amount of stuff. Sorry about that. So let's see. What do we need to do? Well, I need to give you guys that link, so it's going to be right here. I'm going to put it into chat. So this link's actually pretty useful. If you go to the very top of the page, all the way up here, you'll see algorithms for QR decomposition. We are only worried about the very last one, which is the householder transformations, because this is the one closest to the one that we were working on before. Now we have some pseudocode here. And that's fine, but it actually gives us some real MATLAB code at the bottom. Now, with the MATLAB code, we can very easily translate it to C++ code, and it's actually pretty dang close to what we had before. So the big thing is that I'm fairly convinced now that I had the columns and rows mixed up. Rather, maybe I didn't, but maybe I did. I'm not sure. So what I want to do is I want to test eigen. Let's see, if it's row major. I don't really know what row major means. So I want to test eigen real quick to make sure that I'm actually reading things out and writing things the way I think I'm doing it. And if I'm not, then I clearly see a problem and I see a couple things that we need to fix. So let's go ahead and cd into projects. Then Simuleos DMRG. And we're going to cd into projects. Oh, sorry, projects, Simuleos, and DMRG. Okay, and also, I think I can just do it this way. Eigen matrix. Let's see what we got here. Matrix. Let me see. Where are we? Here we have VM01. Nope. This is not at all what I wanted yet. Oh, here we are. Here's a block M1122. Nope. Now the matrix that. Nope. I just want to read out a value. That's all I want to do. Read out a value. And bottom left corner. Nope. Let me see. Okay. Never mind. Let me just go ahead and do this my way, because it's not worth it. This is too much effort. Okay, let's go over here. Utamo, during my linear algebra class, I was like, what the hell am I ever going to use this stuff for? 1.5 years later, it's the core stuff for modern control theory. It is, in fact, very useful. So here's what I'm going to do. I'm going to go into a new file, which I'm going to call check.cpp. Okay, I'm going to do this. Check.cpp. Now, what am I going to do? I'm going to add in a little guy here, a little guy there, and then I'm going to say purpose. Oh, if I can spell purpose. Checking. Let's say things. Checking the eigen library. Okay. And that should be about it. So the only thing I really want to do in this entire file is check to see if eigen what I'm really bad at this, guys. I can't remember how eigen calls data out, so I need to check that out real quick. Okay, so here's what we're gonna do. I think it's naturally row major, so I think that means we're going down first and then to the right, but I'm not sure. So here's what we're gonna do. We're gonna do include IOStream. Then we're going to include eigen, if I can spell eigen, slash core int main, and then we're going to do matrix 17 matrix 2D, and we're going to call it check mcheck. Okay, we're going to say mcheck of, we'll do 0 0. Oh, how about we do it this way? How did we do it before? Mcheck. Let's go here. Let's go into VI. What is it going to be? Eigen. No, not eigentest. Is it eigentest? Probably eigentest. Eigentest. Okay, that's what we want. So mcheck. Let's do. How about 1, 2, 3, 4, and then semicolon. Okay, now let's do std cout mcheck of, what do we want? Let's do the first row and the second column. So this should be a 2. And then let's do, oops, sorry about that. This should be a 2. And then we're going to put in a tab. And we're going to try mcheck of, what do we want? Let's do 1 0. And this should be a 3. End line. Okay, let's write this. Go over here. Write quit. Now we're going to run the last G++ command, which may be up there a little bit. So let's run G++ here. And then instead of Lanzos, we're going to go up here and change this to check. Matrix 2D should have a capital here. G++. Matrix 2D was not declared in the scope, probably because we need to do eigen. G++. Matrix 2D was not a member of eigen. Let's go up here. Using namespace eigen. G++. Matrix 2D was not declared in the scope. What? Eigen matrix 2D. Oh, is it a lowercase d? Is that my problem? Okay, that was my problem. And it is 2 and 3. Okay, so it's going down first, then to the right. Good. Done and done. Sorry about that, guys. I had to make sure. I always get confused at which is row major and which is column major. I know that it's typically row major goes down first and then to the right. So it's usually row by row by row and then column by column by column. But again, it still gets confusing to me sometimes. So what do we need to do today? Well, first I'm going to get a sip of water and then we're going to continue working on what we worked on yesterday. So we'll see how far we get. Okay, so if you're coming in late, which some of you guys might be, I do have an official or another code that we're working with today. And I wrote this code down in my lab notebook. Sorry about, man, I keep hitting my desk. It makes noises when you guys hear it hit the desk. So anyway, I've got that written down and we'll be working on that in a bit. The main background that you need to know, let me see, I passed at linear algebra, remember, like a third of it. Honestly, the thing is, when it comes to linear algebra, I don't know, I'm really bad at linear algebra. It's, differential equations, I was okay at, but man, linear algebra, geesh, I was really bad at linear algebra. It's not anything that comes intuitive to me, so if it's not intuitive to you, just know that it's fairly common for it not to be intuitive. Anyway, what do we need to do? Well, the basis of QR decomposition comes from, in this particular case, what are known as householder transformations. So let me see if we can think about this in another way. Woody Vance, I thought you were a mega genius. No, I'm nowhere near a mega genius. I'm basically, of all of the physics students I've ever met, I feel like I know less than most of them. I mean, that's objectively not true, but it's how I feel like, you know? Objectively, I know I'm a pretty good student, but I'm not that great. I know that one, Wataka and I. That one's from France. Welcome. Thanks for coming in. Okay, what do we have here? Householder transformations. So that's the main thing that we need to talk about today. However, I'm super duper bad and do not fully understand what the householder transformation is doing. My best understanding is that we have some sort of what's known as a hyperplane. Now, a hyperplane is like a simplex, except the opposite of that. So if we have, let's say, a three-dimensional space, a hyperplane will be a two-dimensional space in the three-dimensional space. So it'll be one dimension less, whereas a simplex is usually one dimension more. Now, the idea is that we have this hyperplane, and with this hyperplane, we are creating some orthogonal, vector, and then we're flipping over that orthogonal vector. So we're simplifying the system, creating a vector to flip around, and then by doing this, we create another tridiagonal matrix that can be solved. Now, I looked into this, and I'm still not sure I fully understand it. So hopefully we can start to understand it as we go through it today. Now, we've got a couple choices of how to do this. And I think what I'm going to do is I'm going to write out the code in pseudocode for now. In, what is it going to be? It's going to be in Zernal. And then we'll go from there. 1 second, Zernal. Okay, so let's go ahead and start doing this. Man, I feel like, I don't know. Okay, so pseudocode. Pseudocode of the QR decomp. Okay, so one thing I have to mention is, again, this is coming from the link I just sent about 15 minutes ago in chat, so I'll put it down one more time just so you guys have a link to it. But this guy down there at the very bottom of the page went through QR decomposition with householder transforms. So here's the idea. I don't understand the physics on this channel. So in this particular episode, it's more math than physics. Good, so you should be able to get this one just fine. So the thing is, for the most part, without physics or without math, you cannot do physics, right? And so for the most part, if you're doing math, right? Or if you understand the math, you can't understand the physics. The problem is approaching it in the way that makes it understandable, you know? So like physics is in some sense applied mathematics. Anyway, QR decomposition. What are we actually doing? Well, we start with the loop. It's going to be for j goes to n, where n is the size of the matrix. And it starts at 1. So j equals 1. Oh, that was a 1 equals 1. J equals 1 to n. J equals 1 to n. Okay, pretend I can write this. Okay. Now we say s, which is some sort of sum, is going to be equal to 0. For I equals j to what they say is mj. But this is again just the length of maybe, I'm not sure I fully get the, I don't know if I fully get it, /Pariah, but maybe that's true. Okay, so we have for I equals j to m. Then in this span, we're we're in an n by m matrix. So we're an n by m matrix, which means we are let me see, 1 second. N columns. I think it's an m by n matrix. There we are. So we are m rows and n columns. So see, is that right? M rows, n columns. I guess that has to be right. No, that doesn't make any sense. Wait a minute, let me think here. I thought I had it, but now I think I'm messed up. If we're initializing an n by m matrix, oh great, let me see, what are we actually initializing? Let's go online. Here's the document I gave you guys, and as you can clearly see, we are initializing an m by n matrix, which means we are m rows, so we're m down, and we are n to the right. So what are we doing? Let's just go ahead and see if we can draw this out correctly. So let's go over here, back to the page we were on before. So we're an m by m matrix, which means we're going m, one second, n. So it's n this way, m that way. So for j is 1 to n. So we're going all the way along that way. And then m, we're going all the way down. Okay? Now we say, wait a minute, I'm not sure I fully understand. So why are we going down the lower diagonal? That's what we're saying here, right? So this is saying that if we're going from j1 to n, we're starting at 1. And I think MATLAB naturally starts at 1 instead of 0, so I think that's starting at 0, and that's fine. But here we have for I equals j. So let me see. For I equals j. So that means, yeah, so we're having an I loop, and we're saying it's starting at j. And if j is going this way, then if we're at the first element, then we're counting all of the elements down here. So basically this first guy is going down the lower diagonal, which I find really weird. And this is the thing, I don't get why we'd be going down the lower diagonal, because in the end we want the upper diagonal. But I guess that's fine. Let's go through and see if we can figure out this out. So the first step seems to be going along the lower diagonal, which is different than the code that we wrote. So that's one fix that we need to change, or need to do. Okay, so now we say S is going to be equal to S plus AIJ squared. Maybe that's a little bit more true. I'm not sure. Okay, so now we're going to say S is going to be equal to the square root of S. And this is something, square root of S. And this is something we do have in our code. S is equal to the square root of S. That is totally what we have in our code. Okay, so the next thing we say DJ, D of J is going to be equal to, and what do we want to say? It's going to be equal to negative S or S, depending on AJJ. So if, and so this is, I don't know how to put this. This is depending on the sign of AJJ. So these are depending on the sign of AJJ, where AJJ is again along the diagonal, and we're going to say that, what do we want to say? If AJJ is greater than 0, this is going to be negative, so it is the opposite of the sign of AJJ. Okay, so now DJ is equal to that. Now they create a variable called FAC. I don't know why it's called FAC, but that's what they call it. It's going to be equal to the square root of S times S plus absolute value of AJJ. Okay, now what's next? They say AJJ is going to be equal to, hey Solidbird 454, how are you? It's going to be equal to AJJ minus the diagonal. Okay, so far we're not so far off of what we wrote before. This is actually pretty dang close. Okay, so now we have AJJ is that. Now I'm going to split off into the next page. And in this page what we're going to say is for, and remember we have a big for loop up top. So we're going to say for K equals J to M. Again, going along the lower diagonal. We're going to say A, one second. Okay, we're going to say A of KJ is going to be equal to A of KJ divided by FAC. So what are we doing here? It looks to me like we are fixing the lower diagonal. Like we're setting it equal to something. Okay, so that's equal to that. Or rather, not setting it equal to something. We are scaling it in a way. Okay, so the next one we're saying for, let's say, I think that's an I. 1 second. Has to be an I. Why would I have written down a 1? I wrote 1 equals J. Where are we? Let me go up here real quick. Again, this is a document I linked before. If you don't have it, let me know, and I can give it to you guys. So for K equals J. What? Oh, it's the same loop twice. I see what I did. Okay, that's fine. Where are we? Here are we there? And let's pop down here. So, then we're in the same loop. Sorry about that, guys. And in this loop, we're going to say A of K. I think it's K I. No, shoot. Dag nabbit. That was my problem. Okay, let me scroll back up again. Sorry about that. This is again in this same document. I just wrote something down wrong. So for K to J, for I equals J plus 1. What do we have here? Yep, that's what we have. So for I equals J plus 1. What am I doing? Here we are. Sorry about that. So for I equals J plus 1 to N. So now we're going along this way. And we're starting with whichever one we're on, and we're moving successively that way. So let me think. Yeah, this should be okay. So, what do we have here? We're going to set S again equals 0, and this is kind of like a sum guy. Then we're going to say for K equals J to M. S is going to be equal to S plus A of Kj times A of Ki. And then we're going to say that A of Ki is going to be equal to A of Ki minus A of Kj times S. Okay? And then we end all the loops. So end. I don't care how I end them, so how about I just do this? For pseudocode ending diagonal along that way. They're all ended. Okay. So, what does this mean? Well, basically, guys, this means that my initial assumption that I did yesterday, where I think we can remove the lower diagonal at the start, that was incorrect. In fact, I think we need the lower diagonal from here on out. So because they also do this thing, where they, after creating the lower diagonal, or after going through and working with the lower and upper diagonal, they then go through and they set things explicitly to 0 later. So they take only the upper diagonal of the matrix and things like that. So what I'm going to do is I'm going to do this one more time, except this time I'm going to follow the script a little bit more closely, and we're going to see if we can go through here. Now, because we have the MATLAB code to deal with or to work with, this should be a little bit faster, and we're going to see if we can get this to work right. Now, that said, this is still a pain, and we should just be using the natural eigen QR decomposition stuff. But this is, well, a way for me to learn how to do this, so I think it's worthwhile. So let's go into vi lanczos.cbp. Now we're actually going to start getting into the code itself. And you'll notice, well, if you're paying attention, you'll notice a few things that are a little bit different about the code that I've written and the code that we should have written. So let's go through and let's fix everything up. So the first thing we need to do, for s equals 0, for I equals j to m, let me see, what are we? For j equals 1, here we are. So we have I equals 0 to I equals row num minus 1. And I think that should be fine. For the most part, that should get us to where we want to go. So I'm going to remove this minus 1 here, and we're going to see what happens. So we're going to say that s is equal to the norm of a j to m. Now let me see something. Does eigen have calling specific rows? Because if we have a way, actually, why don't we just do this? Let's go here. Hey, guest friend. And let me do this. Let's do, how do we do this? Let's do vi check.cpp, and let's just check some stuff over here. So let me do check. Let's do, how do I want to do this? Let's do :1. I don't think I'm allowed to do this, but I want to see what we got. Hey, Watakanai. Oh, you said, hey, Gus, and you were also here before. My bad. So let's go over here. Let's run the last G++ command. And yeah, I figured that wasn't allowed, but I thought I'd try anyway. So since that's not allowed, we're going to have to do this the long way, but that's perfectly okay too. So landsauce.cbp down here at the bottom. So the first thing that they do is they normalize all of the points along, 1 second, what do we have here? It says J2MJ. Now again, I don't like, it's row I, column I. Wait, what? I don't know exactly what you mean, Gustman. Is row I, column I. So it's row for, yeah, it's row centered. Okay. Or row major, or whatever it's called. Okay, so let's go through here and let's work on this. So where are we? We are here, QR decomposition. And we can probably get rid of the scale R thing, because I think I did it incorrectly anyway. Now the thing is, they only scale the matrix from J, wherever we're at. What did you want to do again? That's fine. It's fine. The thing is, I realized yesterday that I think I was doing everything backwards. I think I was doing everything as if it were column major or something like that. The idea here is that they actually want to go along the column, I think, and normalize it. Whereas I wanted to go along the row and normalize it. So I think that's the difference here. These guys seem to be going, they write this. They write A. Let's go over here real quick. They want to normalize the following. I'm going to put it up here in the corner. A of J to M J. So that's going to be, let's see, the whole column after J, and then the J row, right? So this is the idea here, is that we're grabbing, let's say here is our guy. We're grabbing all of these elements down here. And that was the thing that I did wrong. So yesterday I thought, because it was an n by n matrix, the code that I was working on before, I thought we were trying to grab all the elements over here. And I think I was wrong about that. So I think we need to grab all of the under elements. So I think at the very end of yesterday's episode, I realized that might have been a problem. And I tried to fix it in kind of, well, one way, but it didn't seem to work. So I need to basically go through and switch all the indices and work it with it from there so that we have everything set correctly. So that was my bad, but I think this should solve things if we do it this way. So that's the idea. Okay, so where are we? We are here. So we don't need the scale R anymore. I think this is okay. So let's go ahead and remove it. And then we'll get back to it in just a second. So what do we need? We actually need a couple of these guys. So let's DD this. Let's go down here. We need those guys. And we also need this Boolean thing at the bottom. So I'm just going to leave those here. And we might get rid of this entire block in a bit, but I'm going to leave it for now. We don't need to remove the lower left. So again, this is another thing that I will leave for now, but probably delete later. And actually, guys, just so I make sure I know it's commented, I'm going to put these here. Here and there. Okay, good. So what do we have here? Matrix, C diag, row number. That's fine. So let's go through and let's get this done. So the first thing we need to do is normalize along the column. Okay. So how are we going to do this? Well, we're just going to go through the entire, well, basically what's left. Now, if you guys remember from yesterday, here, give me just a second. This is actually what the guide we were working on told us to do, but I was kind of too stubborn to do it. So it's going to be 4. Now I'm going to get the indices kind of mixed up here from what's on the document I gave you guys. And again, if you don't have a link, just let me know in chat, and I'll put the link again in chat. So the first thing we need to do is find the max value and divide everything by that. So we're going to say 4. Let's see, we're already at I, so we're going to say j, one second, j equals I. Then we're going to say, oh, I need to probably put an int up here. Maybe remove that. Okay. J is less than, in this case, row number. Then plus plus j. And so this is normalizing along that column. And now we're going to go through and we're going to work on it. So what we need to do is we need to, first of all, find the max value. So this is going to be exactly what we did up here. It's a super simple thing to do. No problems at all. So we're going to say max value, max val of I. One second, let me think. Max val of I is going to be equal to R of II. Okay, and now we say, oh, we should probably do that up here. Max val of I is going to be equal to, that was just to check whether it's row major or column major. That was all I needed to do. That was it. So I checked. We're good. Okay. So what do I need to do? Is going to be equal to R I. I meant to check off stream, but I kind of ran out of time, so I wasn't able to do that. So we're going to say if, what is it? It's going to be R of what should be IJ. No, wait. Are we actually going along the column? Or are we going along the row? See, this is still not clear to me, which one we're actually going along. I'm going to assume we're going along the column. Because again, man, I hate this freaking, linear algebra is a pain in the butt. Okay, so I'm going to assume that we're going along the column. Okay, so if we're going along the column, then what we need to do is we need to say R of J I is greater than max value. Then we're going to say max val equals RJI. Good. Okay, so let's see. Is that what they actually have here? RIK? That is actually, I think, what they have here. So maybe that's correct. Okay, so now what we're going to do is in here, basically we're going to create another loop. We're going to say, well, first of all, we have to throw up an error if things are not going the way we planned, but I think it should be fine. So what they do is they say, you know, we pop up a cout message or something like that. So we're going to say if, let's see, what do they have? S is equal to the norm. Okay, so they create a vector that's called S, and they go through, I'm not sure. Anyway, so let's just do it this way. So we're going to say if, where's our singular stuff? If, what do we want? Max val equals 0. Then we're going to say that we're going to cout, std, cout. And what are we going to see out? Matrix is singular. Do not use. It's fine. We could probably end the program here, but that's fine. We'll see what happens. Okay, so now what we need to do is we need to actually scale everything. So the next thing, we say else. Oh, never mind. This was already done down here. My bad. And in fact, let's go ahead and put the sum up here. sum equals 0.0. Okay, that's fine. DD, and what do we need to do next? So this is all done there. That was my bad. We do this is equal to that. That's fine. Okay, so now what do we need to do? The next thing we need to do is we need to actually set everything up appropriately. So what they do is they say for, well, basically the same loop we had before. So now let's do the actual normalization. So here, let's say find max value along a column. Find max value along column. Oh, I am just an idiot here. Okay, so let's go down here and let's do this. We're going to say, what do I want to do? Normalize column. And it's going to be the same loop as we had before. This guy right here. So let me copy that. And then let's add some spaces in. Okay. Now we don't need this inner stuff. All we need to do now is we need to say R of, it should be JK or JI is going to be equal to R of JI divided by max value of I. And I don't know why I put a parenthesis there. Okay, so let me check again with the online documentation that we're looking at. And it looks to me like this is correct. So it should be the inner loop, which is J, and then the outer loop, which is I. Good. Okay. I know I realize I'm mixing up all the J's and I's and K's and stuff like that, but I don't know. I feel like it's cleaner when it's I on the outside, J on the inside, and K on the very inside. It just makes sense to me. Okay, so now the next thing they do is basically the same loop again. Let's see. So they say, as you see out, this row is the following. I don't need to see out that. Well, maybe I could do this column is. Now I just realized this is the exact same as the other one before, and we already had it right here. It's just with the indices mixed up. So let's go ahead and put this here. I'm really doing a bad job of reading the code before writing. I apologize for that, guys. And we can just go ahead and get rid of this, I think. Yeah, that should be fine. So now we're cououting the column. And let's do JI. Now, what they do is they say sum is going to be plus equal to, let me see, where are we here? They say, where are we? If s equals 0, they say sum should be something plus something squared. I know they do that. For J to M. Okay, anyway, we're going to do that. So it's here, sum plus equals, yeah, here we are, RJI squared. And they say IJ, so that's going to be, oh my gosh, I don't, one second. Everything's kind of screwy here. So the sum is going to be equal to, where are we here? Square root of RIK. So this should be RJI, I think. Oh, I don't know. Anyway, guys, so today's going to be another one of those days, I think, where I'm just kind of messing around with this. So let me know if you have any questions, comments, concerns. And my opinion is if we don't get this done today, we're just going to use a stock QR decomposition method. There's no reason to write it again well, there's no reason to try it again for another day if we have screwed up 3 days in a row, basically. So that's going to be that. Now, what do? We need to go through and we need to define everything else. So if you look at the MATLAB code that is, again, on the documentation thing that we have over here, here it is. Basically, the ideas that they do, scroll down to the MATLAB thing, which is right here. So they have, they do the normalization, which is what we just did. They check for the singularity, which again is what we just did. And then they said, if AJJ is greater than or equal to 0, we set DJ, which is a diagonal, equal to this, right? So negative S or positive S. So it depends on, let me see, if AJJ is greater than 0, dj is, wait 1 second, dj equals negative s. Okay, so depending on the sign of the diagonal, we set this value up as the sum and stuff like that. So s is equal to the normalization of aj to m. Maybe I'm not sure what norm does. Maybe norm also does a sum, in which case we would be fine. So let's assume that it does a sum too. Okay? And then we should be okay. Absolutely no problems there if norm also does a sum. And I think we'll assume it does. So let's go down here. And what do we do from there? Well, we've already done this and that. So now we have the sum here. And we output the sum. Then we say our check is going to be equal to I. That's fine. Now, sigma is going to be equal to the square root of the sum plus double times the sign of r. This I think we're actually going to leave because I think this helps us, or this works pretty well. And then we're going to say rii is equal to sigma. We're going to say that the c diag is equal to sigma times r times rii. And again, this should be fine. And c diag is equal to negative max value times sigma. That should also be fine. Now, what are we doing down here? We say for j equals I plus 1, j less than row number, j plus plus, or plus plus j. This should also be done correctly. I think this is fine. Now, in the code that you'll see online, or in the MATLAB code, you'll see that they have something called FAK, F-A-K, and that's basically equal to our sigma. So they say it's square root of sum, where sum is going to be equal to s plus the absolute value, or s times the square root of s times s plus the absolute value of a jj. So it's along the diagonal. And what do we have here? We basically said we're multiplying it by double times the sign here. So sigma, oh wait a minute, maybe this is dramatically different. I just realized this might be actually a good bit different. Okay, so what do we want to do then? We have the diags here. Let's go ahead and change this up to match the MATLAB code because I trust that more than the C++ code. So let's go ahead and comment this guy out. And let's go that here. Okay, so what are we going to do? Let's actually comment out these C-outs too, because I don't like having the C-outs there. Okay, so the next thing they do after doing this, they say sum is going to be equal to the squares here. And then that's going to be their S value. And they're going to say, let me see. If A of JJ is greater than 0, let's do it this way. If, what do we have? R of II is greater than or equal to 0. Oh man. We do the following. And then else. Gosh darn it. We do this. Okay. Now what is it that we're actually doing? We are going to be going through here and we're going to be saying D, so diag, of I is going to be equal to negative, what is it? Negative sum. Yep, that should be okay. And now we're going to go down here and we're going to say diag of I is going to be equal to sum. And I forgot a semicolon. And again, guys, if you have any questions, comments, concerns, let me know. And I will totally talk about them as soon as I see them come up. Hey, Riodoba, how are you? For some reason... Wait, what? Oh, there's a negative sign up there. We're fine. I was worried that this guy was not aligned to this guy. Like, clearly, this sum at the very end is one column over this one here. And I was like, wait, why is that the case? It's the same equation. And then I realized there's a negative sign up here. So this is going to be one of those days where I'm incredibly tired and I'm clearly writing bad code. But that's okay. So we do this. Then after that, we say FAK, which is something that they created. But we'll call it that too. It's going to be equal to the square root, SQRT, of what is this going to be equal to? S, so the sum, times, what do we want here? We're going to say the sum plus absolute value of, hey Gavelbart, RII. So we have to close that one, and that one. Good. Let me go up here and let's go ahead and define what fac is. Double here, it's gonna be double. So why do I have 2 semicolons there? Fac. Sure, not a problem. Okay. So what do we have here? C diag. Fac is equal to square root of that. So the next step that they do is they say RII is gonna be equal to what do we want? Now they write down, and let's see, or rather I wrote down, okay, this is what I mean then. It should be R of I minus diag of I. Okay, so this is setting it along the diagonals. Now the next thing we do is another one of these weird normalization things. So they say A from J to M J is going to be equal to A to J, or A from J to M J divided by fac. So what we're doing here is another one of those normalization guys. So let's go through and do that. So we're going to say for size T, J equals I, J less than row number. Then we're going to do plus plus J. Go down here. And what we're going to say is 1, 2, 3, 4. I just stopped by and caught that section where you wondered what norm is. And it seems it's a spectral norm in MATLAB Octave, special norm. I had to look it up on Wiki. It has something to do with the eigenvalue of a matrix. Ah, dang it. I'm going to have to look it up too. So let me see. Norm. MATLAB. Vector and matrix norms. What do we have? Norm. Norm of V returns a 2 norm Euclidean norm vector. Ah, that doesn't help me. What do we have up here? What did I say? It said that S is equal to the norm of some array. So we're going to say norm. Yeah, this doesn't help at all then. Dang it. Let me see. Does Julia do the same thing? So let's say norm and Julia. Linear algebra. Minimum norm. Vectors and Julia. Norm. Let's go norm. Okay, that's fine, but I want norm or distance, norm. Yeah, see, that's what you expect the norm to be, square root of x squared. Okay, what do we have here? It says the norm. No, I think it's fine. It should be the L2 norm, I think. So square root of x squared. That's my guess. I'm gonna leave it. Square root of x squared, that's what I'm guessing. And then if this doesn't work, we'll work on it from there. Let's do open link. I'll take a look at this. Let me see. L2 norm. Yep, that's what I expected. L2 norm. Okay. So what are we going to do from here? Well, where are we? For size T, J equals I. So what they're doing is they're going through each of these guys, and then they say A of J to M J divided by fac. So this means that we're going to be going through, just like we did before, R of J to I. What do we want? R J to I, and then we're going to say equals R J to I. That should be fine, I think. So this is going through each of those. Wait. Yeah, so this is going through everything we'd expect, divided by their value, which they call fac. Okay. So now let's go through and let's see what else do we need to do. The next thing we need to do is do transformations on the rest of the matrix. So we're going to say if that was fur. I don't know why I wrote fur instead of if, but if j is less than n, which is going to be row number, so it's always going to be less than n, so we don't have to worry about this if statement. We then go through. Well, yeah, that's fine. Let's do it again. So if j is less than... Now there's no reason to. It's like, it's fine. It's fine. It's a square matrix, so we don't have to worry about this if statement. Okay, so then we say a, so r, of j to m, so we're going to say 4. And let's see what we have down here. Because what they do is they say from A from J to M, and then J plus 1 to N. And then it's going to be equal to from, oh gosh, this is super complicated. Here, let me just show you the code. Here we are here, and they say the following. A from J to M, J plus 1 to N. A from J to M, J plus 1 to N minus A J to M, J times A J to M, J prime times A J to M, J plus 1, N. Okay. So the prime is the transpose. So we're basically creating a vector here and doing the transpose of that. So let's see, how do we do this in C++? Well, let's see. Yeah. So let's see, what do we have here? 4. dk is equal to negative sigma. So it's going to be 4. We need some sort of big for loop that goes from, I guess, J plus 1 to N. Okay. Then we say, we basically create some sort of, okay, wait. It's from J to M, J. So how do we create matrices from other matrices in eigen? From other matrices eigen. My Google foo is great today. Advanced initialization. I want to make a vector out of a matrix. So what do we have here? Vector is equal to that. Vector 2 join. That's fine, but that's not what I want. Special matrices and array. What do we have? Output. Nope. Output. These seem to me, like they're just adding all of the different matrices together. But that's not what I want. I want to grab specific elements and create a vector. So top left corner, bottom left corner. That's fine. These are all just joining. Yeah. Usage temporary object. How about creating a vector from a matrix? From a matrix eigen. Okay, eigen, all matrices and vectors matrix. Vectors are just special case matrices. That's fine. Coefficient of the matrix vector of an array. Nope. How do you make a matrix out of vectors and eigen? Maybe? No, that's exactly not what I want. How about colon operator? Eigen. Okay, so function similar to MATLAB and octaves. Yeah, let's see what we got here. Sometimes instead of using lin-spaced, it would be nice and more convenient, lin-spaced, to have an expression similar to MATLAB's colon. Suggested dense space range. What about introducing more general range object that would specify in different ways? Sized range, stepped range. This is different than what I was expecting. I thought there'd be an easy way to do this, but I was incorrect there. So let's see, where's the code again? So here's the code that we have to write. If j is less than n, which is fine, it'll always be less than n in our case, we'll then say, in fact, it'll always less than n in their case too. Anyway, we'll say a from j to m, j plus 1 to n, is going to be equal to a from j to m, j plus 1 to n. So these are the same indices. Subtracting out a from j to m, j times a from j to m, j prime times a j to m, j plus 1 to n. Okay, so all of these indices are the same. This guy's the same, that guy's the same, this guy's the same, except for these guys right here. So a from j to m, j. So let's see, how do we get these guys to match up? So it should be then that these guys are going from j to m. They're all starting from j to m. That's fine. Then we say j times whatever these guys are. So this is going to be individual elements there. So I think what I can do is I can create two loops. One that goes from J to M, and another one that goes from another variable that goes from K to N. Oh, is there such a thing as a submatrix? Let's see, what do we have? Let's do submatrix eigen. Nope, that's not what I wanted. Block operations. Well, good. Let's see what happens there. So what do we want? Block in the middle. Oh, okay. Well, they seem to be able to do that just fine. So M block 2211. Okay. So what we need to do is create a block. Okay. And where do we find M? M is equal to that. See out M block. Okay, so let me try something real quick with our test guy. So let's go over here, right, quit. Let's go to check.cpp and let's create this a matrix XD object. Yeah, I got that one, Galvabart. I was trying to figure out how the indices made sense. So we're going to do XD here, and then we're going to do M check there. And what we're going to do is we're going to say 3 up here. So it's a 3 by 3 matrix. And we're going to say 4. Then we're going to say 5 and 6. Comma here. 7, 8, 9. Okay, so the 3 by 3 matrix. Now let me see if we can figure something out. So what I want to do is a matrix XD, and we're going to say block. Okay, and we're going to say is that matrix. Oh, that was meant to be a 7. I don't know how I got a T out of that, but now it's a 7. So we're seeing out M check. That's fine. This should be okay. Let's not worry about this right now. Now what we need to do is figure out this block stuff. So up here, I capitalize an A for no apparent reason. And let's go down here and see what we need to do. So it should be m.block22 of 1, 1. So this should give us 5, 6, 7, 8 if we do that. So we're going to say block is going to be equal to matrix.block. So we want M check. And then let's std cout block end line right here. 1 second. Okay. And then we're going to do g++ check.cpp. Let's see. I forgot a comma here. Okay, what do we have? Need an extra one there. Okay, g++ seems to work. Segmentation fault, fantastic. Okay. Let's just go ahead and do this then. Let's say, let's not read it into another matrix. Let's just make sure it works without reading it into another matrix. So let's do this, and let's do std cout mcheck, and then we're going to add in a semicolon or a end line. Okay, we're going to delete this. Over here, g++, a.out, segmentation fault, fantastic. Okay, what do we have? Am I doing something stupid here? mblock22. Let me see. For int I equals 1, block of size 2, 2 is going to be 1, 2, 5, 6. That's fine. It's starting from 0, 0 to 1, 1. Or, yeah, so let's go here and let's try this again. Except instead of doing it this way, let's try this way. So we're going to do 0, 0. So it's starting at 0, 0. And let's do 1, 1. Go to g++, a.out, also segmentation fault. Fantastic. Okay. So they're doing the same thing we are. They're creating a matrix XF, M, Let's see. What is the difference between these two? Oh, maybe it's because I don't have the right. Maybe if we do eigen include eigen dense, maybe. So let's do g++. A dot out. Dang, what is the deal? So they have matrix 4 4. Screw this. I'm gonna copy this exact thing and see if it runs. Because I am a sad, strange little man who can't figure out how to work with eigenvalues. Or not eigenvalues. I can't figure out how to work with anything. Okay. Write this, go over here. G++. See how it was not declared. Yeah, that's fair enough. One second. Okay, so now we're going to do G++. Included. Okay, let's change all these end lines to these guys. Okay, and at some point, this should work. I'm just not sure when. Okay, so let's go here, and let's do G++. Runs just fine, A dot out. Okay, that one works. Now the question is, why didn't our other one work? So let's go up here. Maybe it's because I didn't define how big the matrix was supposed to be. So let's do this. Oh, that wasn't what I meant to do. Okay, so we're going to do G++. M. What did I do before? Oh, oops. G++, A dot out. Yeah, okay, that was it. So it was because I had forgotten, or I did not define how big M was. So this should be fine if we use something like this in our code. So what we should be able to do then is, unless I'm completely wrong, is with the block guy, we should be able to completely replicate what they have in their MATLAB code, except in this case with C++ and eigen. And that should be okay. I'm not so worried here about keeping it C++ syntax. In fact, I should have just done this in Julia or something like that, but that's beside the point. Okay, so what do we have here? We have this guy, and let me see, do they have a norm in eigen? Is that what we have over here? Oops. Norm eigen. They should. I would imagine they would. Did I already Google this today? Maybe I did. Okay, so let's go down here. Where are we? We are here, I believe. So we just divided everything by fac, and now they're on the next step. So it is, where are we? Oh, we're down there. The following. So now we have to create a whole bunch of different blocks. So let's go ahead and do that. We need one block, which is the matrix from J to M along the columns, and then J plus 1 to N along the rows. Then we're going to say A from J to M, J plus 1 to N, so the same guy, is then going to be equal to different guys. So now we have to create some blocks to work with. So let's go here. Yeah, that's fine. Creating blocks to work with. And let's go up here and define them. No, I don't think we're going to be able to define them beforehand. I think we're going to have to define them here. So we're going to say that we didn't check something. That's probably essential. So let's go over here. Let's go back to check.cpp. And let's see if we can define, let's see, block 22 of 1, 1. Let's see if we can define this as something. So let's go down here. And let's say we're going to do matrix xf. And then what do we want? We want block equals, how about, I don't care, q is going to be equal to m dot block of, this one's easier to make, so 0, 0, 1, 1. And now let's go down to the bottom and std. Std c out q and line. Okay, we're gonna do g++, a dot out. Okay, well that one, block of size 1, 1. Block in the middle, block of size 1, 1, block of size 2, 2. This wasn't exactly what I thought. So let's maybe do 2, 2, g++, a dot out. Okay. So I guess we're grabbing two elements. We're starting with 0, 0, and then we're grabbing two elements in X and two elements in Y. So that's what we're doing there. And it seems to work just fine. So let's go here, right quit. And now we're going to do landsofts.cpp. And let's go through and create all of the blocks we need. So we already have the J elements we need to be on. Let me see, where are we? We are up here. Gosh darn it, this is going to take so much time. But that's okay. We're learning, or I'm learning anyway. And again, guys, if you have any questions, comments, concerns, let me know, and I will totally address them as soon as I see them in chat. Okay, so what's the next step? We need to create the blocks. So the first block we're going to call block 1. So we're going to say matrix xd block 1. And it's going to be equal to, let's see, r dot block from, yes, so we want it from a starting position. In this case, it's going to be a starting position of J, J, I believe. So it'll be J, J, so we're starting at the center, and then we're going to be grabbing all the way down here. Let's make sure we're doing this right. So over here in our previous code, we say 0022. I want to grab two elements down, but I don't want to grab any elements to the right. See what happens if we do this. We're going to do g++, a dot out. Yeah, okay, I figured there wasn't going to be anything there. So we want to grab only one element. One element here, right and quit. So now we're going to do g++, a dot out. So that gives us one column, vi check.cpp. Now I want to try something else. Let's start at element 1, 1. Okay. And then we want to grab two elements down, one element to the right. So this should give us a 610. G++, a dot out. Yep, that gives us a 610. So what we want then is, let's see. It needs to be columns first and then rows. So we're going to say, we're going to grab J minus M columns and then 1. And this should give us some sort of column in that direction, which I think is exactly what we need. Yeah, that's what we need. Okay, so we're going to take this, and now we need to create a second block, which is going to be down here. We're going to say matrix xd block 2. And this is going to be equal to, let's see, it should be A from JMJ. Let's see, J plus 1 N. Wait a minute. J from J to M. One second, I'm trying to think here. So we're grabbing all the elements, starting from JJ. Oops, I got these guys mixed up. I don't know how, but I did. This is actually the second block. The first block is going to be matrix xd block 1, and it's going to be equal to r dot block. And which element are we starting on? We are starting on element JJ, or JJ plus 1. So j plus 1. And then we're going to element j minus m. And then, let's see, j plus 1 to n. So that's going to be j plus 1 minus n. But in this case, these guys are all the same. So let's do a row number here. And row number here. And row number over here. Okay. So let's see. Is this what we actually want? I don't know. So let's go here and let's do std cout block 1. Let's see, block 1, new line. I'm going to need 2 new lines. Then we're going to do block 2. Okay. Now, the next bit is where we basically go through and we say, we do the multiplication. So we're going to say block 1 is going to be equal to, and this is where I think something's going to screw up. It should be block 1 then it's going to be minus, and then this is j to m, so it should be block 2 times block 2 dot transpose. Then we're going to multiply that by block 1. Okay, so that is all they do here. So I'm going to go ahead and comment all this guy out. All the way up to here. Hey, Lucky Box. What's your name? You guys all know my name, I thought. I know you've been here before, so okay. My name is James. I am a student at the Okinawa Institute of Science and Technology. Good. Okay. So what do we have here? The next thing is now we have to do some explicit setups and stuff. So here, since all this is backed up on Git, I'm going to go ahead and remove a lot of these lines that we don't need. We can always revert back if we need to. So let's go here. Let's go here. And let's go down here and delete all these lines. This just makes the code a little bit cleaner. And again, it's all on Git, so it's not that big of a deal. I just realized I need an additional guy here. Okay, so now the next bit. We do. Hey, Lucky Box. Okay, so the next thing we do is we say, well, what they do is they go through and they create another function, right? So they have this function to do the function that we just wrote, to do the QR decomposition, and then they do another function entirely to work on some other stuff. But I'm just going to kind of write this all together. So they read in a matrix, and then they also read in an element called y. And this is the thing that kind of confused me about the other guy too. They just kind of randomly introduce elements, and I'm not sure what they mean. So what are we going to do? Well, first we perform the previous guy that we just did. So now we do all that. Now what we need to do is explicitly set up everything else. So again, I'm going to kind of just delete all this kind of stuff for now. And let's see if we can do this right. Oh, okay, good. Okay, so let's go here. DD. Now, what's the next thing we need to do? So now we need to set up some different things. So we've already returned back, or we've already changed the array to what we need to change the array to, right? So now what we need to do is we need to go through and create some sort of identity matrix from particular points. Now, one thing I don't like about a lot of linear algebra, numerical linear algebra, is they call The identity matrix I as in EYE, it's kind of weird. I don't really fully understand why that's a thing, but it is. So that's okay. So now we have to kind of follow a similar route as to what we followed before. We're going to say, we already have Q initialized, I believe. And it should be initialized as the identity matrix, I think. What we need to do for I equals I. Yeah. So let me go over here and let me take a look at this. So the next thing that they do is they say, we create a function here, and they say from m to n, we have the size a, and we set z equals y. Y is something that we read in. And then we say for j equals n, incrementing -1. Sorry for the yawn, guys. And then we go all the way back to 1. Now we say z of j to m is going to be equal to z of j to m minus a from j to mj times a j to m j prime times z from j to m. And then they do the main program here. So I is equal to I of mn. Q, they initialize it there. Then they say for I equals I. And this is the thing, I'm not sure exactly what's happening here. For I equals I. What does that mean? What is this notation saying? That I'm not sure. I'm going to get a quick sip of water real quick. Quick. I'm apparently super redundant today. Sorry about that. Okay. Again, I'm not really sure what this notation means. And I don't have access to MATLAB to really check. So, let me see. For I equals I, z. So, I is a matrix, right? So, for I equals a matrix, right? What is that saying? Are we going through each individual element in the matrix? Or are we going through... See, I'm not sure. I think from up here, y needs to be a double. But again, I'm not sure. So here, z equals qy. Yeah. So let me see for loops. MATLAB. And let me see if they go through an array. So let's go array. No, of course not. For loop. For I equals array. MATLAB. Oh, column of vector in MATLAB. For element equals list. That's fine. Let me think. For I 1 to length of list. Also fine. See, that's fine, but what for a 2D array? Nope, that's not what I want. 2-dimensional array. Iterating, how do you make a 2D array? Iterating through 2D array MATLAB. So for size E, that's for IDX 1 to numel array. No, I just want... Nope. None of these are what I want. I just want to see what this notation means. Maybe I should just download Octave and just deal with it. Okay. Let me see, how big is Octave? Doesn't really tell me. That's okay. Let's see, now it tells me. It's going to be 14.37 megabytes. Let's do it. Dagnabbit. Cancel. Sudo pacman syy. Octave. 1. Yes. Okay. Let's do it. Come on. Doesn't take that long to update a man page index. That's super quick. I was expecting that to take a while. for n step n, for k step n array nk. Okay. For n equals 1 step n. Yeah, I get that one. And n. That's what it's doing. So let me see. For n array, what does n array do? For k equals 1 step octave. I don't want any of that. No, I don't want you to connect. 1 second, guys. Finish. Wait, why did you open up? I didn't want this. I didn't want that at all. Before. Octave, no desktop. No Windows system. That's fine. For n equals 1 step n. How do we open this up? Octave. 1 second. Okay. From the command line. Let me see. Normally Octave is used interactively with a running program. Octave, Octave help, Octave. Okay. This is like even less useful than no Windows system. Okay, that's fine. No Windows system should work for now. I just need to figure out. Okay, this is what I want. Now let's do what they say to do, which is where are we? Here. Okay, for I equals I, so I is going to be equal to IMN. So let's just grab this line here. And we're going to say I is going to be equal to 3, 3. Okay, now we're going to say for, what did they say? I equals I. So let's go here. For I equals I, print I. I wonder if that's a thing. And okay, maybe just for I equals I, and okay, so we're creating, unless I'm wrong here. Okay, so what you're saying over here is for n equals 1 to step to n, k equals 1 to step to n, array nk equals 1 or whatever. But it seemed to me like these guys are just going through and pulling each column. That's what it looks like. So I think that's what we need to do. We just need to pull each column. Okay. So it ended up being, I think that this was way more complicated than it should have been, but that's okay. Okay, so what we need to do is we need to create an identity matrix that is of the appropriate size, and then we need to create blocks for each of those guys and read them in to the appropriate function. Good. So let's go here and let's say creating or explicitly defining Q, and let's go ahead and create the identity matrix. So I think Q is already the identity matrix, so we're going to say that ID. Oh, do I already have identity defined up top? Let me see. What do we have? Matrix XD, identity. That's fine. We're going to call it matrix XD ID. ID is going to be equal to the same exact thing as we have before. There. Okay, now we're going to go down here. Yeah, I'm not sure. Again, it's just I'm running off of someone else's code, so I'm not sure exactly why they chose to do it the way they did. But my guess is that we need each individual column, and I think that's true. So let's go here. Okay, so what I need to do is create a block, or let's say, what on earth? Creating column block for multiplication. Okay. Now what do we have here? Z equals Y, size A, MN. Z from J to M. Yeah, so it has to be a column, I think. It is a column big. Okay, yeah, I think that's fine. Yeah, okay. Good. Thanks, Frankie, for chess. So what we're going to do now is we're going to say matrix XD block. Yep. XD. And we're going to say... I'm sorry, Frankie, for chess. I'm hoping things get a little bit easier for you. And we're going to say block. What are we going to say? We'll say ID block. And it's going to be equal to, what do we need? We need to grab individual elements. So we're going to say 4. I guess size T. 1 second. T. J equals 0. Then J is less than, what do we want? J is less than num, where are we? Row num, sorry about that. Then we're going to do plus plus J. Okay. Add in a semicolon there. And we're going to say the ID block is going to be equal to, it should be ID of, what do we want? ID of J. And then it should be the entire column, right? So it's going to be J. And then it should be, I would think, 0. So let's do J0. And then row num 1. Okay. So we have that guy. Now what's the next step? We say, yeah, so we read that in to the loop that they've created. And now we do a negative indexing loop. So we create the initial row. Then after creating the initial row, or the initial column, we then go through and we perform the following. So we say 4 size T. Actually, it's going to have to be an int. K equals row number. Then we're going to say K is greater than 1. 0. Then we're going to say minus minus K. Minus minus K. Negative indexing for the win. Now we go down here. And what do we need to do? Well, we already have created the row for this particular group, I suppose. So what do we need to do next? For some reason, they keep redefining a Z factor here, and I'm not sure exactly what that means. So, yeah, let's see what happens. So it's going to be Z from J to M. Okay, so they say that Z is going to be equal to Y. So it's going to be matrix XD. Z is going to be equal to ID block. Okay. Now they say Z from, they say J to M, which is their internal loop. So this is going to be from, I guess it would have to be, let me think, how are we going to have to do this? Z equals ID block. And then we say, I guess creating additional blocks for multiplication. So, and they say Z from J to M. Man, this is super complicated. Way more complicated than I wanted it to be. Z from J to M. Z is equal to Z from J to M. Let me see. All of these guys are going from J to M. So I think we should create an additional loop on the inside here. Nah, shoot, that doesn't make any sense. Yeah, this is totally not working out the way I wanted it to. Let me see. How are we going to do this? we can okay, again, guys, the code is available here, and this is the problem I'm having. This guy right here, 4. So it's z from j to m is equal to z from j to m minus a from j to m j times a j to m j transpose times z from j to m. I can perform that multiplication, I think, just fine. However, after performing that multiplication, I'm not sure what exactly is happening here. And then the other thing is, I'm not exactly sure what's happening here either, because we say 4 I equals that. Oh, we end it here. What is up with this loop? 4 I equals this, it ends there. Okay, whatever, that's fine, indenting aside. And I also don't know what the tree U thing does. I don't know what this is. So we'll have to figure. Oh, it's upper tri. It is the upper triangular matrix. That's fine. I get what it is now. I don't know what proof is though, so that's something we have to look into later. Okay. So let's go through here, and let's do it. Okay. So we're gonna say creating blocks. Okay, so let's do it. We're going to say matrix xd z. No, I guess z block. Why not? Really good at this, guys. Z block is going to be z dot block. Where are we? Did we do the identity block right? I'm sorry, dot block. And then z dot block. And what are we going to grab? Well, there's only one element, so we're going to have to grab, let's see, what do they want to grab? It's going to be j to m. So in our case, it's going to be k 0. Then what do we want to grab? We want to grab, let's do k minus row number. Row number minus k. Hey, pants for birds. Row number minus k. And it's okay. Don't worry about it, man. We're kind of just playing around as always. 1. So that's going to be our z block. Now the next thing we need is the matrix. This is not going to compile, by the way. Matrix xd. And what are we going to call this? This is going to be called the, I don't know, what should we call it? We should call it R block. Doesn't matter. Is going to be equal to R dot block. And what are we grabbing? We're going to be grabbing A from J to MJ. So this is going to be KK. And then we're going to be grabbing, let's see, row number minus K. Minus K. And 1. Yep, 1. Okay, now we perform the multiplication. And what do you do for 2D matrices in C++? I've been able to decide if I should use nested vectors, 2D arrays, or I should roll my own class. Actually, Pants for Birds, what I've been using lately is just the eigen library. It's a pretty useful linear algebra library. It works relatively well. If you're using a whole bunch of linear algebra stuff, I would go with that. However, if you just need to do simple two-dimensional matrices, you can do a vector of a vector or whatever you need to do. That's fine. The 2D arrays also work. You know, it just depends on what you want. Oh, yeah, there you go. Okay. So what do we have here? Performing the actual multiplication. So what we're going to say is z block is going to be equal to the z block if I can spell Z block, minus, and what do we want here? It's going to be R block times, and this should be R block transpose blocks. No, I don't think there's an easy way to do this. So let's just create another loop, which is crazy that we have so many nested loops, and I'm terribly sorry about that. Actually, this should be okay. So we're going to say for, dang it. Yeah, we can do it element-wise. That's what I was saying. So for int, yeah, we'll do int k equals 0. And I'm going to fix the uppercase in just a second. K less than row number. And then plus plus k. I could. However, the thing is, I need to add basically like the very last element of a vector. Like I only need to add to specific elements. So it's actually easier to do this. Yeah, two different matrices together. Okay, so what are we going to do? Let's change all the j's to i's, because I like having i's on the outside, just because it makes it easier for me to understand what I'm doing. Let's see, row num 1 should be fine. ID block, so now we change all the k's to j's. This is going to be super messy and it's not going to compile. It's not going to compile at all, I'm pretty dang sure. Row num minus j. And j. Now let's go here. What do we want? R block.transpose, Z block. Should be okay. Now we do this and we say if k is greater than, oh, why don't we just do it this way? For k equals j, now we're going to say Z block equals Z block of, sorry about that, should be k is going to be equal to Z of k is going to be equal to Z block plus equals Z block of k. Okay. So now we have all our z's and everything, and that should be that loop. Now we need, actually it should be both those loops, all three of those loops actually. Whoa, getting crazy. So what do we need to do next? We then need to say that at the end here, after going through each of these loops, if you do one day a week where you use them so the code is colored, I will not be using colored code, not on this stream. I'm already super frazzled when streaming. It's not exactly the easiest way to code. And then with colors, I would not be able to do it. There's no way. Like I would just freak out. We tried doing that actually like a few months ago, and I just could not do it with colored code. It just drives me nuts. Okay. So now at this point, we need to say that Q, and again, this is according to the page that we had before, Q is equal to QZ. Okay? It's not the easiest thing to do. I mean, I'm not saying like it's incredibly difficult and you guys should, you know, like, I'm not saying I'm doing a good job, nor am I saying it's incredibly, incredibly difficult, but I am saying that when you're trying to talk about what you're doing while you're coding, like the coding mindset is completely different than the, you know, like I'm talking to people mindset. So you just kind of talk about what you're doing. Okay, so the next thing we need to do is say that Q is equal to QZ. Now, the thing is, I'm not exactly sure what this is doing either. So let's go over here and let's open up Octave one more time. Oh, we already have it. So we have I is equal to I. So now let's say that I, yeah, which happens a lot. So we're going to say that, let's say U is going to be equal to, and then we're going to say 0, 0, 0. There, that should work. Now we're going to say that Q is going to be equal to, I, U. Okay. So that does that. Which means that basically what we're doing here with this Q guy is we're going through and we are making it not square, which I don't like. Then we say Q is equal to... Okay, so I guess we'll do it. Now, there is a super easy way, adding blocks. Eigen. Misspelled eigen. Misspelled it again. There we are. Okay, so we have block of size 2, 2. That's fine, but I want to add them together. See, this is the thing, like, we had this page up a while ago on stream. No, not that one. We had the page I'm looking for up on stream not too long ago. But I don't think... Matrix constant... I don't think I have it anymore. Oh, maybe I do. Oh, here it is. So what are we doing? We are saying... where are we? Do we actually use Q? QZ. No, okay, so it looks to me... Okay, so this is actually fine then. What we say... I wish these libraries would share notation with Fortran or MATLAB. I think the matrix operations in those languages is very intuitive. Yeah, it's pretty easy. That's one reason why I like Fortran a good bit. But that's okay. You know, we're working on it. So actually, guys, what I need to do is I need to set the first row in... sorry about that. I need to set the first row in the Q matrix equal to Z. That's what they're actually saying we're doing here. So let's do that. So we're going to say Q of, what do we want? Oh, dang it. Join. Here we are. Okay. So join vector 1, vector 2. Let me see. Joined. What do they define join? Okay, so row vector 7. Is it possible to do inline Fortran in your C++ code? I'm not sure. I actually have no idea. It's not something I've tried before. So vector 1. Let me see. Is there another join here? No. Let's say joining or... Oh, I bet you I can do this. So we're going to say Q. Oh, that wasn't what I meant to do. So we're going to say Q of, what do we want? We want... No, that was my problem before. Dang it. I want just the first row, right? So if I just want just the first row, then we could do Q. I'm not sure how this is going to work. So let's go here. Let's right quit. Let's go into the check.cpp file and let's output something. So let's std cout, and I want to see out m of 1 end line. Let's go over here, Control D, and now we're going to do the last G++ command and run a out. Okay, 6510. Let's see, what is that? 6510. Oh, that's not right at all. M. Let's output m of 1, 2. G++. A out. 6710. 610, 7. What? What is happening? Output Q. Q is equal to m block. That's fine. M of 1. So that means we're going down 1. We're going over 2. That's 7. 610, 7. Oh, I see what's happening. Okay. No, so in any type of Linux or Unix system, if you type in !G, it'll pull up the very last command in your history that started with G. So in my case, it's G++ I whatever. So if I run history, you'll see I have 554 in history. So if I run !G, it's going to run G++. If I run !O, it's going to run Octave no Windows system, which it did. So it basically runs the last command. So if I run like V, it's going to open up check.cpp, and that's because in my history, the very last command that was !v was vi check.cpp. Yeah, it'll work on any Unix or Linux-based system. So anytime you have a terminal, you can totally do that. Yeah, no, it's one of those things. There's a whole bunch of weird tricks that you just kind of get used to if you use Linux a lot that you don't really think about or use a lot if you don't use it a lot. So what I wanted to do is grab an entire column. So let's do G++, a.out, 5. What are we grabbing here? 1. Why is it only grabbing one element? That's okay. So I want to grab an entire column. So let's go here. Pulling a full column from matrix eigen. Block operations. Maybe this is what I want. And block 2. No, I don't think this is what I want. Array A. Nope. A.block. Columns, vectors, ith row. Oh, okay. So I could probably just grab m.col of 1. Go here, G++, a.out, and 2, 6. Yep, that's what I want. Fantastic. So let's go here and go to landsaz.cpp, and we're going to say q dot, what do I want to do? I guess dot call of j. Q dot call of I is what I want. It's going to be equal to, at the very end here, we should have a zk to work with. And let's see, id.block. Yeah, so we should have qcall is going to be equal to z. Is that it? I guess so. Maybe that's it. Okay, so that's that. Now, moving on to the next step. We have our queues defined. Now what we need to do is use the upper triangular matrix. So now we have to explicitly remove lower left from R, which is actually what we had before, but we're going to do it again. So for I equals 0, then we're going to say I less than row number. And then we're going to do plus plus I. Okay. Now we're going to go up here. And we're going to say big R of I is going to be equal to D diag of I. And then we're going to say for. And up here I need to put an int. We're going to say int j equals 0, j less than I. Then we're going to say j plus plus, or plus plus j, doesn't matter. Okay, and here we just set them all equals 0. R of I j equals 0. Okay, so now we have the R matrix done. But we only really care about Q. And Q is going to be transpose of what we have. So let's just return Q dot transpose. Okay, I'm going to compile this and we're going to see what happens. Here's the last GPP command. So now let's change this to lanzos.cpp. And we're going to have a whole bunch of errors to fix. Okay, so, not as many as I expected. That's okay. So let's go to 186. And it says if rji is greater than max val, invalid operations of types eigendense coefficient base. Wait, what? Is greater than max val. If rji, one second, I'm thinking here. If rji greater than max val, incompatible types assignment. Eigendense coefficient base, double, -1, -1. Let's go to 215. Because that's an easy one to fix. Okay. Error. Z was not declared in this scope. 249. Z. Matrix X. D. Z. Oh. Oh, that might be Y. Okay, what do we have here? When you're doing this kind of coding, which seems to be more for learning, how often do you write tests if you use them all? Well, here on stream, I don't do so many tests, but for research code, yeah, I'm getting into the habit of writing more and more tests. Tests are incredibly useful, but again, it kind of depends on what you're writing it for. So these codes are usually only like a couple hundred lines long, so it's not so important that we have tests with them. But if you have codes that are a couple thousand lines long, then it's super important to do tests. It seems to me that the number of tests that I write is proportional to the size of the code. So as the code goes up in size, the more I want to test it to make sure I don't have to, you know, worry so much about little things. Okay, so R is going to be equal to expected semicolon before R. Yep, did that one. J was not declared in this scope. What do you mean? 221. J was not declared in this scope. Oh, crap. These are all I's, I bet. Going with it. They're all I's. And I just realized those are backwards, actually. So this needs to be row num minus I. Yeah. I have some rather big code that I'm working on lately, so I've been implementing some unit tests there. They're not very good, but I've been trying to get into the habit. I figure you do a decent amount of testing for your thesis code, but I figure that these are more fun projects. You wouldn't need as many. Again, so if the code is... My rule of thumb now is that if the code is over 5,000 lines long, I should have some tests for basic features. But that said, it's probably not at the same scale as a computer scientist would do with testing. So it kind of depends. Minus I. And then I row number. I think it's going to be row number minus I plus 1. Okay. So let's see, is that right? Maybe. Now what's next? J is not declared in the scope. 249. What do we have here? It says QI equals Z, but Z is totally declared in the scope. Matrix XDZ. Maybe it's because I didn't define it out here. So let's go up here and define, how do we do this? Matrix XD Z. And it's always going to be of size. No, it's not. We'll just do this. And then let's go down here and say Z is equal to ID block. Actually, wait, this is always going to be of a particular size, and that size is going to be row number 1. Okay, let's try compiling it one more time. Okay, we got similar errors as last time. What do we have here? 183. I don't know what to do about the incompatible types assignment, so let's fix the other ones first. 257. 4, of course, I forget a semicolon, and J was not declared in the scope. Is that because I forgot the semicolon? Okay, good. So now let's go ahead and clear a couple times. And let's do G++. Okay, so now we just have to fix this one. I started a pretty massive project, at least for me, and I've spent more time writing tests than code. Yeah, it depends. So in my opinion, I gotta get some code done every day. And I think tests count as code, so, you know, that's how it goes. Incompatible types in assignment of eigendense coefficient. Okay. So, this is the thing I have. I'm not sure exactly why it's not letting us set values. So let's go here. Let's go into vi check.cpp. This is totally going to break when we run it. Okay, so what are we going to do? We want to set a particular value equal to something else. So I'm going to try doing that over here. I'm going to say m of, and we're going to do 1, 1 is going to be equal to, let's set it equal to 5. Now let's go over here and let's run less g++ with check.cpp. Now let's run a.out and let's see, 2, 5. Yes, okay. So this one seems to work just fine. So it's clearly something we have wrong in our other code. So let's go into CPP, sorry about that. And now let's go up here and let's see what we get. It's saying we have invalid operands type eigendense coefficients base, eigenmatrix double double, scalar aka double, and double row number. To binary operator. Okay. So how about we try something else? Incompatible types assignment. Max val is equal to r. Okay, so where are we? We are on line 186. So it's not going to let us for some reason. I'm not sure why it's not letting us do this. So here's the thing. RJI should be a double. However, max val of I is equal to RII. Yeah, let's just do that up there. Oh, this might be why. This guy needs an I. And this guy needs an I. They were blind, but now they see. Right here. And let's do G++, lens out to CPP. And at 6:59 in the morning, just before ending stream, we break the code. Okay, so guys, we did most of the writing today. I'm gonna go through and I'm gonna see if we can do some, I'm gonna see if I can do some quick debugging tonight. I think this code makes more intuitive sense. Tomorrow, we'll spend the first hour fixing this up. Again, we spent, I think, way too much time on this, but that's okay because this channel always ends up meandering some way or the other, so it's not that big of a deal. However, we are almost done with this, I think, so we're gonna see how far we get. I'm going to try to get tonight some sort of working code version up. I have some stuff to do tonight, but I think that's okay. I should be able to get it all done. So I'll work on this maybe during lunch and after work today. But at this point, we did most of the writing. I think what I'm going to do is I'm going to commit this to GitHub. But again, it's not quite working. Obviously, it's broken. I really should have a beta branch in GitHub, but I don't. Oh, well, that's okay. At this point, guys, it's 7 o'clock in the morning. I realize we spent the entire day recoding up something that we recoded up yesterday and the last time we did this, but again, that's how it goes sometimes. So anyway, guys, thanks so much for watching. Have a great day, night, morning, afternoon, evening, whatever time it happens to be your time. And I will see you guys around next time where we finish this up for good. Even if it's not working, we're going to finish it up for good. I'm just going to move on to another way to do the diagonalization because it's not worth it to spend that much time on this. And then hopefully, by the end of today, tomorrow, we'll have a diagonalized matrix, and then we can just work on the next part of the algorithm, which is actual dense matrix renormalization group, which is how we do the, how we do the manipulation of spins and things like that. So again, today is Tuesday morning. Tomorrow will be Wednesday morning my time. And then hopefully on Thursday morning my time, we will be officially working on DMRG. And we'll see how far we get. And that's about it. So again, thanks guys for watching, and I'll see you next time. Bye guys.